Welcome to UXL, where you can learn new skills anytime and anywhere. Visit uxl.com to explore our full course selection. This lesson is part of a larger course. Check the video description below for a link to the full course where you can enroll. If you enjoy our content, please like and subscribe. For your convenience, the course cover displayed on your screen provides the complete course title and lesson title. Let's proceed with the lesson. Lesson: Cross-validation and model generalization. Cross-validation and model generalization are pivotal concepts in the realm of machine learning, especially within the context of model testing and validation. These methodologies are integral to the development of models that not only perform well on training data, but also exhibit robustness and reliability when applied to new, unseen data. The significance of these processes is underscored by their ability to mitigate overfitting, enhance model performance, and ensure that models can generalize beyond the data they were trained on. Cross-validation is a statistical method used to estimate the skill of machine learning models. It is particularly useful when the amount of data is limited, and it allows for a more accurate assessment of a model's predictive capabilities. The most widely used form of cross-validation is k-fold cross-validation. In this approach, the dataset is partitioned into k equally sized folds. The model is trained k times, each time using a different fold as the test set, and the remaining k1 folds as the training set. The model's performance is then averaged across all k trials to produce a single estimation. This technique is beneficial because it ensures that every data point has the chance to be in the training and testing set, thus providing a comprehensive evaluation of the model's performance. The effectiveness of cross-validation in preventing overfitting cannot be overstated. Overfitting occurs when a model learns not only the underlying patterns of the training data, but also the noise. Such models perform exceptionally well on training data, but poorly on unseen data. Cross-validation helps identify overfitting by providing a realistic estimate of the model's performance on new data. This is crucial because a model that generalizes well is one that maintains its predictive power across different datasets. In addition to k-fold cross-validation, there are other cross-validation techniques such as leave-one-out cross-validation and stratified k-fold cross-validation. OOCV is a special case of k-fold cross-validation where k equals the number of data points in the dataset. While it provides a nearly unbiased estimate of the model's performance, it is computationally expensive, especially for large datasets. Stratified k-fold cross-validation, on the other hand, ensures that each fold is representative of the entire dataset by maintaining the same distribution of the target variable in each fold. This is particularly useful for imbalanced datasets where certain classes may be underrepresented. Model generalization is the model's ability to perform well on new, unseen data. Generalization is directly linked to the model's complexity and the amount of training data available. Simple models may underfit the data, failing to capture the underlying patterns, while overly complex models may overfit. The balance between bias and variance is critical in achieving good generalization. Bias refers to the error introduced by approximating a real-world problem, which might be complex by a simplified model. Variance refers to the error introduced by the model's sensitivity to small fluctuations in the training set. Cross-validation helps in identifying the right level of complexity that minimizes both bias and variance. Regularization techniques, such as L1 and L2 regularization, are often employed to enhance model generalization by penalizing overly complex models. L1 regularization, also known as lasso, encourages sparsity in the model by adding a penalty equal to the absolute value of the coefficients. L2 regularization, or ridge, adds a penalty equal to the square of the magnitude of the coefficients, which discourages large coefficients but does not necessarily lead to sparsity. These techniques reduce the model's complexity, thus aiding in better generalization. The success of a machine learning model is not solely determined by its accuracy on the training data, but by its ability to maintain performance on new, unseen datasets. This is where the true test of a model's usefulness lies. A model that generalizes well can be trusted in real-world applications, providing reliable predictions that guide decision-making processes. An excellent example of this is in medical diagnostics, where models must accurately predict outcomes for patients not included in the training set. Cross-validation, in conjunction with other validation techniques, provides a framework for ensuring these models are robust and reliable. Incorporating cross-validation in the model development process also facilitates hyperparameter tuning. Hyperparameters are the parameters of the learning algorithm itself, which need to be set before training the model. Cross-validation provides a robust mechanism to assess the impact of different hyperparameter values on model performance. By evaluating the model's performance across multiple folds, practitioners can identify the hyperparameter values that yield the best generalization performance, thereby optimizing the model's predictive power. Furthermore, cross-validation ensures that the evaluation metric used to assess the model's performance is robust and reliable. Common evaluation metrics include accuracy, precision, recall, F1 score, and area under the receiver operating characteristic curve. Cross-validation provides a more stable estimate of these metrics by averaging the results across multiple folds. This is essential for making informed decisions about model selection and deployment. In conclusion, cross-validation and model generalization are indispensable components of the model testing and validation phase in the GenAI lifecycle. They provide the necessary tools to ensure that models are not only accurate, but also robust and capable of performing well on unseen data. By leveraging techniques such as k-fold cross-validation and regularization, practitioners can build models that strike the right balance between bias and variance, leading to improved generalization. The insights gained from cross-validation allow for better model selection, hyperparameter tuning, and evaluation, ultimately leading to more reliable and trustworthy models. As the field of machine learning continues to evolve, these foundational concepts will remain critical to the development of models that can effectively tackle a wide range of real-world problems. This concludes the lesson. We trust you found this video informative and engaging. To enroll in the complete course, please use the link provided in the description below. At UXL, we are committed to your learning journey. Each course offers a certificate of completion, online support, and downloadable resource files to enhance your experience. If you found our content valuable, we invite you to like this video and subscribe to our channel. Thank you for joining us, and we look forward to supporting your continued pursuit of knowledge.